Thanks so much. Thanks so much, Camila, for the invitation to speak. And yeah, also for the correct Spanish pronunciation of my last name. So not always possible, but super nice. And yeah, so I'm really happy to share with you all the work of our latest preprint in this mediation method for time to event outcomes using pseudo-values. Really, the motivation for it, as you'll see, is to provide a easily interpretable, simple to estimate approach for mediation analyses and for time to event outcomes, which can be tricky. And I'm going to present an application as well to a clinical trial in multiple sclerosis where we actually applied the method so you can see it in action and see kind of the interpretable inferences that you can make using this method. And again, yes, I'm Alex Ocampo, and I'm in the statistical methodology group at Roche in Basel, in Switzerland. Okay, but first, huge acknowledgments to my co-authors. Our preprint is online, and we just finished our second round of revisions at minor revision at biometrics, so you should see that coming in soon. But you can read the preprint in detail here. And yeah, huge thanks to my co-authors. Everyone played a significant role. This is by no means a solo work. And not just to this fantastic group of co-authors, but also many others that gave us comments and had good provoking questions along the way. You know, some very much in a presentation like this, a simple comment turned into a nice added contribution to the work. And so very much looking forward to any questions or comments that you as well. Okay, so just the key points that I want to make throughout the talk. The first is that just more generally, that mediation analysis is a powerful method from causal inference that can help us to explain treatment effects. So especially in clinical trials or causal inference more generally, we try to see if there is a causal effect, but mediation allows us to say how that causal effect actually manifests itself. So it's a very powerful tool. The second is about this direct area that we're in. This problem we're trying to solve is mediation analysis for time to event outcomes. It's trickier than for other outcomes. And our proposed pseudo-value mediation method, our aim again is to provide a simpler, interpretable alternative to existing mediation approaches with time to event outcomes. So that would be the bulk of the talk. And then lastly, again, I'm going to show this data application where we're going to mediate the total effect of a treatment, fingolimod, on clinical relapses. That's a clinical measure, and we're going to mediate that. We're going to show how this biomarker, gadolinium-enhancing T1 lesions, is a mediator that we establish or help establish on the causal pathway between treatment and the clinical symptoms. So that's will be the general outline of the talk, as well as the key points. Okay, so let's get into the motivation for mediation and just a quick background for what it is in case you're not familiar. So just causal mediation analysis in a nutshell breaks a total causal effect of some exposure or treatment A on an outcome Y into two distinct components. The first is the indirect effect. This is the portion of the causal effect that flows through the mediator. So this dark blue pathway here. And then the direct effect is this arrow directly from A to Y that it quantifies other pathways that don't flow through this mediator. So that's really what we're doing. We're breaking down a causal effect into its components, one that flows through the mediator and not. And when M and Y are continuous variables, this is a very simple thing to do. You can just fit two regressions. You can first regress this outcome Y on both the mediator and treatment. So you can see this model here. And then the coefficient on the variable A corresponds to the direct effect, this light blue pathway of A on Y. And so you can interpret this beta A as this direct effect. Then to get the indirect effect, you fit a separate regression where you regress M on A, and then this coefficient alpha A here quantifies the effect of A on M, and if you combine this with the beta M here, which quantifies the effect of M on Y directly, then you can multiply them together to quantify the entire indirect effect pathway. And so that's probably the simplest form of mediation analysis that was introduced by Barron and Kenny in their seminal 1986 paper. Now, if you add the direct and indirect effect together here, you recover the total effect. Again, it's a decomposition, so that's good. And a really nice interpretable quantity that's easy to communicate to non-statisticians is the proportion mediated. And you can estimate that by just dividing the indirect effect by the total effect. And so you can say, something like, well, we found that 80% of the effect is mediated, which that's, it sounds like it's really playing a big role. And, versus if you found maybe, 10% the effect is mediated, maybe that's less explaining this of the causal effect. So it's very easy to communicate this kind of statistic. And lastly, what's really important is that, so I work in the context of randomized clinical trials, so I don't have any confounding on the treatments typically. But nevertheless, I have to control for common causes of both M and Y because part of doing the mediation analysis is getting this estimate of beta M correctly, and that can possibly be confounded. And so we need to control for potential confounders of M and Y, and we do that by including those in this outcome model here. And of course, that's a no one observed confounding assumption, and so we need to be aware that we're making untestable assumptions when we're doing mediation analyses. So that's very important to recognize and say. Okay, so that's mediation analysis. Now, just high level, so that's what it is, but what can it do for us and why is it important in randomized clinical trials, especially? So I think there's kind of three main reasons why I'm personally interested in mediation analyses. The first is kind of what I've alluded to so far is really explaining why a treatment is working. So the clinical trial might answer if it works, but how is it working? Through what biological pathways is this treatment manifesting itself? And can we begin to explain why we're seeing the effects that we're seeing from a biological point of view? And that's, of course, a very relevant scientific question. The second is in justifying a surrogate endpoint. So if you look at the statistical surrogacy literature, you will see mediation pop up as one of many potential methods to evaluate a surrogate. And this makes sense because if you can establish a surrogate on the causal pathway between treatment and outcome, then it's likely to be a good surrogate. So it's another great way to evaluate and compare surrogates, etc. And well developed in the statistical literature. And the last one that I'm not going to talk about for at least this data application I'm going to present, but it's a good application is accounting for intercurrent events. So intercurrent events are often mediators, things like rescue medication use or treatment switching. And so you could apply mediation analyses to intercurrent events to understand how much of the total effect they're actually explaining. And there's a really nice paper by Hege Michels that describes this in more detail. So those are kind of the reasons why I'm personally interested in mediation and why we're seeing an uptick in mediation in clinical trials. Okay, so now that we've kind of motivated the problem, let's get into the direct contribution of our work in this pseudo-value mediation for time to event outcomes. So, but first, just kind of to show you why mediation with survival data is a bit trickier than with other endpoints like the simple continuous one we presented, let's just consider doing a mediation analysis with kind of our favorite tool for regression with survival data, the Cox model. So we could do something very simple. Let's say we fit a total effect Cox model, so we get the total causal effect here, which would just be this beta naught. And then we fit another Cox model where we control additionally for the mediator. So we're kind of blocking the mediator pathway. Now this beta 1 is more representing our direct effect. And so if we just were to contrast kind of beta naught and beta 1, we could kind of begin to quantify how much is being mediated here. So if beta 1 really shrinks to 0, then probably most of the pathway is flowing through M. And conceptually that makes sense, but kind of mathematically or methodologically, there's some problems with doing that. The first is that Thies Lange, who's one of the co-authors on our paper, showed back in 2011, is that due to the non-collapsibility of the log hazard ratio in the Cox model, this kind of negates any causal interpretation if you combine two Cox models together. So they're kind of mathematically inconsistent with each other. So we can't use those simple product or difference methods that you can do with continuous endpoints for mediation. The problem that's probably more of a concern for me, oddly than the technical one, is actually the ability to interpret it. So again, mediation analyses are somewhat exploratory in nature, and when you try to interpret the decomposition on a hazard ratio scale, it can be more difficult to interpret. And just to show you how, take a look at this table here. So this is a mediation analysis done by Thies in 2017. the total effect was a hazard ratio of 0.7. The natural direct effect was a hazard ratio of 0.77, and the indirect effect has a ratio of 0.9. Now, I just ask you, you don't have to answer, but just to eyeball, what proportion of the effect do you think is mediated here? And if it doesn't jump out to you directly, then you're like me, where it also doesn't. And part of the reason why is because on the hazard ratio scale, the mediation analysis is a multiplicative decomposition. So we multiply the indirect and direct effect together to get the total effect, not the additive way that we did in the continuous case. And so actually here, the proportion mediated is 30%. And that doesn't jump out to me, at least, intuitively, but just by looking at it as it might for a more additive decomposition. And so this really motivated us to develop something new and provide mediation methods that are using more interpretable statistics like the RMST and the survival probability. Because again, mediation analysis is an exploratory type of hypothesis generating analyses. And so we want interpretable quantities so we can actually kind of say, okay, is this pathway like clinically meaningful? Okay, so what survival estimands and estimators are we going to consider? So I'll present to you the three different ones in this table. So starting first with the survival probability, so probably the simplest to interpret, right? And we get this from the Kaplan-Meier curve, of course, and has this simple interpretation of just the probability of having survived or being event-free at a particular time t, so let's say 1 year or something. And for the total effect, you can just contrast them with the two treatments. What is the difference in probabilities at 1 year or any time point? And then you get your total effect difference. So now this, if we decompose this, it will be on the additive scale. Now, the problem with that, of course, is that that's a local measure of the Kaplan-Meier curve. And so a more global measure is the restricted mean survival time, which we can get by just integrating under the Kaplan-Meier curve. And it has a nice interpretation as the average survival time up to time tau, whatever that restriction time is at the top of the integral. And so this difference that we calculate here is on the time-based scale. So you can say, oh, you save, 3 months under treatment or 1 year under treatment, et cetera. And so that, again, is an interpretable quantity, which will aid us in interpreting our mediation analyses. And then the last one we set out to mediate was the cumulative incidence curve that takes into account competing risks. So this is, often a problem in something like the cardiovascular trial where you're interested in the kind of time to heart attack, but then you have death or non-cardiovascular death as a competing risk. And so we want to take that into account. So we can do that by doing some sort of like Alan Johansson estimator. And then we get, again, a simple interpretability of the probability of having the event of interest at time t, accounting for the competing risk. And we can just contrast the cumulative incidence curves from the two arms at a particular time, now having accounted for this competing risk. So that's the other one that we set out to mediate. And all of these have many advantages. They all have non-parametric estimators, so no distributional assumptions, no proportional hazards assumption. They're collapsible, they're model-free, and most importantly, as I keep repeating, probably myself, is that they're interpretable, and that's was really the motivation for us. We want to be able to communicate these easily to non-statisticians and medics in order to draw important conclusions. So that's the advantages. I think the big disadvantage is that incorporation of covariates into these, kind of more complex statistical functionals is not so straightforward, but that kind of sets the stage for the pseudo-value, which is going to be our machinery for incorporating covariates, which, as you've seen, is very important in mediation. So if you're not familiar with the pseudo-value, it's actually not a very complicated concept, but maybe an interesting term. What it really does, this pseudo-value, is to try to capture how much the full sample estimate theta hat changes due to a particular subject I. So every subject I has a pseudo-value, and you can generate that pseudo-value for everyone by just using this formula here. And so what it's doing is that it's kind of contrasting the overall estimate theta I of your data set with the leave one out estimate. If I took out that a particular observation and recalculated the survival probability or RMST, whatever statistic I'm interested in. So it gives you a measure of influence kind of that it's having on the overall estimate. And you can kind of see this histogram of these leave one out estimates here that drive the pseudo values. So very easy to calculate. If you can calculate the overall statistic, you can calculate the pseudo value. But why is that interesting? Well, Anderson has a series of seminal papers where they show that if you model the pseudo value in a linear regression model, then the effect that the covariate effects have on the pseudo value correspond with their effect on the non-parametric estimate. So I encourage you to try this out yourself. When I first did it, was very exciting. If you just calculate the pseudo values in a clinical trial and you fit this simple linear regression with just a binary treatment indicator, this beta 1 will correspond to just the non-parametric difference between the two curves. And that's really nice because obviously with a binary treatment, that's simple, but if you have more like a continuous treatment, etc., that you want to regress on a time to event outcome, this gives you a framework for doing this in a principled way. And why this works is because the pseudo value is really an estimate of the conditional expectation of the survival statistic conditional on the covariates. And again, this is often the left-hand side of a regression. And so that's what the pseudo value is really getting at. How much does this statistic move based on a person with a particular covariate value? And I guess we can get that from the intuition of how they're calculated. Okay, so now let's just put all these things together. So mediation, these interpretable survival quantities, and the pseudo values, and give you the recipe for actually performing this pseudo value mediation. So the first step is just to calculate the full sample estimate. So for any given survival estimate, let's calculate the overall sample estimate. Let's say we're doing the RMST. So not separately in treatment arm, just for the overall sample, let's calculate the RMST that we're interested in. So that's the first step. Then calculate these pseudo values. We have the equation here. Just leave one out estimators and then plug them into this. So quite straightforward. Now comes the nice part. So similar how we can use the pseudo values to do regression, we can now use them in these simple mediation models that we would have done had we had continuous data to start with. Because now, even though our outcome of interest is a time to event, we can reframe it as a continuous pseudo value and perform the regression on the pseudo value instead, and then fit the mediator model as before. And if we do that, we can have the same decomposition that we originally had, whereby the beta A from this outcome model in the pseudo value corresponds to the direct effect, and then this alpha A times beta M multiplied together quantify the inductive. So we have this nice decomposition now, even though we're in the time to event setting. And then lastly, for inference, of course, we can do a bootstrap of this whole procedure. And it's very important to do the bootstrap of the entire procedure, not just kind of the model fitting, because you need to regenerate the pseudo values in the bootstrap. But nevertheless, because we're in this kind of like continuous model combination case, we do have a closed form expression for the variance of the indirect effect, and this is based on a second order Taylor series expansion. So we can just also use the formula, which in the simulations works quite well for getting inference. Now, again, another motivation for this, I generally work with people that are quite busy running clinical trials and don't have as much time for these sort of exploratory analyses. So it was really important that I wanted to provide a tool to people that would be easy to implement for them. And so you can see that this whole procedure can be done in just a few lines of code. So in step 1, you fit your Kaplan-Meier curve here, and again, not stratified by treatment, just for the overall sample. Then in step 2, you calculate these pseudo values with this pseudo function. This is in the survival package, so you don't need anything beyond the survival package to calculate this. And you just, in the type argument, you specify whether you're interested in survival probability at this particular time or an RMST with this restriction time tau there. So that's a pseudo value. And then you can plug your pseudo value into your mediation models. And I'm a real big fan of this CMA-verse package in R. It's a very nice, well-done package, very user-friendly. And here you can specify linear models and just put the pseudo value in as your outcome. And then that will perform steps 3 to 5 for you in fitting the models, deriving the estimates, and performing the inference. So it's very straightforward to do. And I should just say that if you're interested in the competing risks analysis, Zach, who's one of the last author in the paper, he has this nice SERV-utils package where you can calculate the pseudo values for the competing risk analysis as well. Now, one thing I want to say here is that actually these functions, these pseudo functions, as well as the SERV-utils for the competing risk, they're not actually doing this leave one out calculation for the pseudo values. They're using this influence function approximation of the pseudo values. And part of the reason why that is because to do these leave one out estimators, especially have a large sample or a bootstrap for inference, it can be very computationally intensive to do all those leave one out estimators. And so this influence of function approximation is accurate and much more computationally efficient. And to understand why it works, if you're not familiar with the influence function, here's just the definition, the formal definition of it. So now we're going to kind of rebrand our estimate of interest theta as a functional. So t is a statistical functional of a probability density function f. And the influence function is defined as the instantaneous relative influence of a particular observation xi on the functional. And so we can see that here in this definition. So you have t of f here, the original functional, and then contrasted with the functional applied to this mixture distribution of f and this delta xi. And so delta xi here is the Heaviside function, which corresponds to a point mass distribution at point xi. Actually, this should be an xi here. And so, and it's a weighted average between f and this point mass distribution, where the weights are these epsilons, and we're taking the limit as epsilon goes to 0. So that's why it's the instantaneous relative influence of xi, because this epsilon is going to 0. And maybe you remember from your first calculus class, but this looks very much like the definition of the derivative. And indeed, this is often called the Gateau derivative for statistical functionals. So that's what the influence function is. Why is that useful to us? Well, Stefanski and Booz show that the pseudo-value can be expressible as something that looks very similar to this formal definition of the influence function. So just with a bit of algebra, you can redirect this, where now this epsilon n is equal to the -1 over n minus 1. And if you take the limit of n going to infinity, so the sample size going to infinity, that's equivalent to epsilon going to 0. And then asymptotically, you get that this is equivalent to the influence function. So if this right-hand side is now the influence function, and you've got the pseudo-value minus the overall sample, you can just add theta hat to both sides. And now you can approximate the pseudo-value with the overall sample plus the influence function approximated at xi. That's all maybe very technical, but the important thing to know is that this allows us to get a computationally efficient way to calculate the pseudo-value. And this is actually what this pseudo function in the survival package is doing. So I think it's important to state this. Okay, so that's the methodology, but now let's get into evaluating it via simulation. Okay, so we have a very simple data generating setup. So we have a binary treatment A, normally distributed mediator M that's dependent on A, of course, and then a time to event outcome that's exponentially distributed, where the rate parameter depends on both the treatment and mediator. And we assume independent censoring for the simulation. Now, one thing that was at first a bit puzzling to us was what are actually the true mediation effects we're trying to target in this simulation study, because they're not just simple combinations or parameters of the data generating mechanism. The indirect effect for RMST, for instance, is defined as such, where we actually need to take the expectation of the RMST over the mediator to define this indirect effect. And this turns out actually to be an integral that doesn't have a closed form solution. So we need to do some sort of approximation. So first we thought maybe we'd do some sort of Monte Carlo integration or something like that. But we found this nice trick that we can actually use this Gaussian quadrature. And we have a follow-up paper that describes a bit how to do this for other simulation settings. You can check out, it's on arXiv now. But the gist of it is that you can rewrite any integral with respect to a normal distribution, which our mediator is normally distributed, as a finite sum using this quadrature. And finite sums are very efficient, and the quadrature is extremely accurate to calculate the true values. So that was just a nice trick to actually give us the targets of the inference that we want to target. Now, how does the method do in targeting those quantities? It works well, I guess, as expected, but nevertheless important to validate. So you can see that this is for the RMST estimates. We're unbiased for the total effect, the direct effect, and the indirect effect across the different scenarios and sample sizes here. The next thing we looked at was type 1 error. So these are QQ plots, or not QQ plots, just like the expected versus observed p-values. They should be normally uniformly distributed under the null hypothesis, and you can see that if they fall on this line, then they're quite accurate. The only exception here is kind of in the indirect effect for smaller samples. We have slightly conservative inference, but that doesn't lead to type 1 error inflation, but could potentially have implications for power and small sample sizes. But this is a well-documented phenomenon for the indirect effect. It's going to make sense because you're kind of combining two estimates together for the indirect effect. But nevertheless, that vanishes as the sample size increases. And sorry, I don't have the legend here, but the dark red is the higher sample size. Okay. So yeah, just in summary, again, maybe not the most interesting thing to go through all the simulations, but incredibly important because we're proposing a new method to validate it and show it that it works. But in summary, I showed you the results for the RMST, but kind of the more extensive figures have also for the survival probabilities, cumulative incidence curves. We looked at different cutoff points of tau, 2, 3, and 4 years, sample sizes, different scenarios where we had direct effects in the different combinations. And then, of course, looking at the different estimates of the direct, indirect, and total effect. And regardless of what we looked at, the method was unbiased and controlled type 1 error adequately across the different scenarios. And of course, that's incredibly important for this new method, especially before we start using it in practice, which is what I'm going to end with, is actually this clinical trial data application, so you can see how you or anyone would actually use this method in practice, and most importantly, what it gives you when you do the mediation in this way. So I'm going to apply this to a clinical trial in multiple sclerosis, which was the area I worked in for almost 5 years in conducting multiple sclerosis trials. And if you don't know much about MS, it's an interesting disease because it's often filed under kind of like, you would see a neurologist and it's neurological, but it really has this autoimmune component. And you can see that in this first figure. So here we actually have a blood vessel in the brain. That's kind of this dark red part, but you can see these black dots here. These are immune cells like monocytes, T cells, B cells that have broken the blood-brain barrier and migrated from the blood vessel where they should be into the nervous system tissue where they should not be. And this causes damage to either the brain or spinal cord or nervous system. And if you do an MRI scan of a person's brain when this is happening, these show up as what are called GAD-T1 lesions. So these white spots here, you can see they show up on the MRI, and this is a sign of this immune activity being in the place where it's not and causing damage to the nervous system. Now, this manifests itself as clinical systems. So, and kind of the mystery of MS is that, or at least in the past, was that it would manifest itself in many different ways because obviously it depends on which areas of the nervous system are being targeted. So if it's something that's affecting the way you move your leg, you can have a limp on one side of your leg. If you're hitting the part of the nervous system that's just purely cognitive, you might move fine, but you're having, memory issues, etc. Or, different organs can have issues. And so sometimes it can be a bit of or at least in the past, before these MRI scans became available, it could be a bit of a mystery to diagnose. But now with the MRI scans and other biomarkers, it's becoming, very clear the biological way that it's manifesting itself. And so we set out to do a mediation to kind of confirm our own understanding of the pathobiology of MS, where we're going to use these lesion counts in the MRI scan as the mediator, and then the time to relapse as our clinical outcome. So before we show the mediation analysis, let's just look at the total effects that we're going to actually mediate. And again, we're looking at interpretable quantities. So first, we're going to measure the time to relapse. And relapses are generally the primary endpoint in relapsing multiple sclerosis trials. And we're going to use these lesions as collected on the MRI scan as the mediator. Now, these scans are taken at year 1, and so we're going to look at the time to relapse up to year 2 as the outcome. And so you can see there's a strong total effect here for the survival probability of having a relapse at the year 2 mark. So under the control treatment, 45% of patients had a relapse at that time and only 15% on the treatment. So it's definitely working, and that corresponds to a total effect or a risk difference of a 30% reduction in relapses. On the survival time scale, now our treatment effect is on the time scale. And so you can see under the control treatment, their RMST is 8.94 months, and under control, 11.29 months of being relapse free. And so the mean relapse free time is extended by 2.4 months over a year under treatment. And that's definitely not an insignificant amount of time. So we start out with an interpretable total effect, which will help us as we do the mediation analyses. So let's look at the mediation analysis using the pseudo-value mediation on the survival probability scale. Remember, it was 45 versus 15%, so we had a total effect of 30%. And we're estimating that these T1 lesions are mediating around 24% of this total effect, and we detect a statistically significant effect from zero there. And so we're mounting some evidence of the T1 lesions playing an important role in the causal pathway between treatment and outcome. We adjusted for a number of baseline covariates that are known to be important in MS, and we did a bootstrap inference, some replicates to get these confidence intervals. Then we also did the mediation on the RMST scale. We can do that as well with the pseudo-values. And what was really cool was to see that the proportion mediated on our RMST scale is around 26%. So very similar to the 24% on the survival probability scale. And that's nice because it doesn't matter what summary measure we use, these analyses are rather consistent with one another. And so I guess like a proper causalist doesn't always care what model they're using. Any reasonably specified model should give us a similar conclusion if a good causal effect is there. So that was nice to see as well. So we got both of those there. Now, someone asked once at an early presentation of this work, well, you've picked this kind of horizon at the year 2 mark. What if you varied this time horizon? And that was a really excellent comment. And so we went back and did that. And what we can see here is that we've got the proportion mediated on the y-axis and the that cutoff time on the x-axis. And so we can see like the closer that we are to the actual MRI time the MRI scan was taking, the more of the treatment effect is being mediated, maybe around 50% up here. And then around kind of the half-year mark, it really starts to drop down. And what I showed was here at the 2-year mark, actually. And so what this gives us an idea is kind of the reach of the mediator and how far out in time does it explain the causal effect that we're seeing. I think this is a real great opportunity for doing mediation with time to event outcomes that you wouldn't get for certain kind of landmark analyses, even if they're maybe simpler to perform the estimation. So this was a really nice follow-up analysis to do. Okay, so I will just end there, and then it looks like we've got plenty of time for questions and discussion. So just to conclude, just want to say, again, mediation analysis generally is just a powerful tool to help explain treatment effects. They can help with these 3 utilities to explain mechanisms of action, justify surrogates, and handle end-to-current events. And we're seeing an increase of mediation analyses in clinical trials. I just saw a mediation analysis in Alzheimer's, in JAMA Neurology a few weeks ago. In the cardiovascular space, we're seeing more of them in clinical trials. And so in causal inference, it's been there for a long time, but kind of this uptake into clinical trials is very encouraging to see these adoptions, especially for me, someone that's kind of like working to popularize these methods. And again, this R package, the CMA virus, I think is a great starting point if you're new to mediation. So I'd encourage you to check it out. Then our contribution is this pseudo-value mediation provides this like simpler approach for time to event outcomes. Simple because you just have to estimate linear models to do the analysis, and the simulations have validated the approach as unbiased for a wide range of scenarios. And again, the key is that this allows you to do mediation on interpretable estimands, and that really fills a gap in the mediation literature where most of the mediation papers are about decomposing the hazard ratio. And then lastly, this clinical application shows supportive evidence of these GAD-T1 lesions being on the causal pathway between treatment and clinical relapses. These are well known to be on the causal pathway from a biological standpoint, but really, at least from the literature that I looked through in MS, we couldn't find a formal mediation analysis that had been done. So it's nice to complement our scientific understanding with this quantitative evidence as well. And I think it's, you might say, okay, well, it's around 25% mediated that you found. And so when I talked to my clinician about this, he was saying, well, actually, I would expect more like 100% to be mediated, but you're kind of hinging your entire mediation analysis at this one time point, this one snapshot. And, maybe if you had done an MRI every day for the whole year or something, you would get a larger mediation. So he was actually impressed that we were able to mediate so much with a single scan. But again, just shows you that mediation analysis, it really hinges on the data you have available, et cetera. But nevertheless, we saw a signal there on both the survival probability and RMST, so that's encouraging. And again, I think varying this time horizon is a really nice thing to do that gives you an idea of like the reach of the mediator and how far in time it actually affects things. So those are the main conclusions of the talk. And yeah, I thank you for your attention. Again, if you want to see the preprint, that you can scan the QR code here. And just a shameless plug. So here's my email here. I'm hiring an intern to work on things related to mediation analysis. So if you know a master's or PhD student who's interested in such things, definitely feel free to get in touch with me. But nevertheless, thanks so much for your attention, and really looking forward to answering any questions or hearing any comments that you have. So thanks so much.